Hi everyone, this is my video number 8. Okay, so for this video I will talk on integral over a general region. Okay, integral over general region. Integral over a general region. Okay, so we talk the region of type 1. So we still deal with triple integral. So in this case, just I want you to imagine that we have what kind of region is this? Yeah. Let's say we have a surface up there, whatever it is. Okay, we have a surface up there, and this surface, let's say, it's a closed surface. Probably we have one more that. Okay, it's a closed surface. Now, in this case, this is the solid that we deal with. All right, and we have to look at in different ways. First thing you have to look at on the z-axis. There's a z function. So we may have like this one is given as z is equal to, let's say, f1 xy. This one z, let's say, given as f2 xy. Okay, now the purpose is that we want to evaluate the triple integral over those region. Okay, so let's call those region as I call it as V. Okay, and we have f x y z dv. Okay, so that's what we want. So this is our function. Now we need to determine the limit of each of these integrals. So for the first integral here, we deal with the z-axis. So in this case, z between two functions x and y. So which means we have this integral. We have z from f2 xy to f1 xy, and then our function fxyz d. Here we have on xy plane, this is z, so means inside there we integrate with respect to z. Okay, so here we have r on xy plane and dr. So what is r then? What is r? Okay, r in this case is that we project those regions solid onto the xy plane. So we might have something like it's overlap here. We might have something like that. Yeah, we project this from z positive. Yeah, project from z positive on the xy plane. Now, if on the xy plane, let's say this function given as y equal to g1x, that given by y equal to g2x. Remember that this function, this s function, continuous on the required solid domain. f1 f2 also continuous on xy plane in the required domain, and as well as g1 g2 also continuous in certain interval. Now, having done that, so in that case, for the second integral here, the first integral, I repeat that, the first integral, we look at the solid. The second integral we look at on the xy plane after you project those solid onto the xy plane. Alright, so having done that, we have now for y we have from G1 to G2. So we have G1 x to G2 x. Okay, we have the third integral as that. This is y, f2 xy, f1 xy. Alright, okay, so f x y z, f x y z, dz, dy, and dx. For dx here, for dx, you look at the sketching that I have here. The limit for x for this integral. Okay, so we look at on x-axis, where is this value? So let's say this value a here a to b. Okay, so which means this integral x from a to b. Now remember that in this integral, the most outer integral, and the most outer integral, the limit must be taken from a number to a number. Okay, a to b, not a function to a function, otherwise you cannot solve the problem. Okay, so in detail, so that briefly that I can explain to you. In detail, we consider a continuous function f. Consider a continuous function f, of course in this case x, y, z, and we consider a solid. Let's call the solid E. Now let's call that solid E. We say solid E is of type 1. If so, we have E is, we have x, y, z, such that for x, y in D, x, y in D, so u1 xy, z, u2 xy. Okay, and D is a region on xy plane that we project like here. Those we project on xy plane. In this case, I call it R. In the theoretical part, it is D. Okay, where D is a point, all point xy, such that y is in between, let's say G1 x, G2 x. Okay, and for x itself, that in the interval AB, let's say I, or maybe I can write, I put it here, so x in between A and B. So you have to look at this in three ways. First, on the z-axis, second on the plane xy, z-axis because we consider space, and then on xy, on plane xy, and then we consider on x-axis. You may consider either x-axis or y-axis, depend on what type of integral or which one is much easier for you to deal with. Let's see the example. Let's say we want to evaluate z dv. This is E, where your E is a solid bounded by x equal to 0, y equal to 0, z equal to 0, and x plus y plus z equal to 1. So if you look at this solid, sketch will give you a good idea to see the region much clearly. Okay, so let's try to sketch that region. Okay, so we have x plus y plus z equal to 0. How to sketch this? First thing, you consider on each axis. So on x-axis, that yz is 0, so we have x equal to 1. Let's say here x equal to 1, and then on y-axis xy is 0, so y equal to 1, so here is y equal to 1, and on z-axis xy is 0, so z equal to 1, so that. Okay, and then you consider on plane. First you consider on the axis, each axis. Alright. Second, you consider on plane. To see how does the curve look like on each plane. So for that, on plane xy, we have z is 0. Okay, look at this. Z is 0, so you have x plus y equal to 1. So this is a straight line with a negative slope, intersect at 1 for x, 1 for y. So we have a straight line. That. Okay, this line is x plus y equal to 1. Now consider on xy plane. On yz plane, x is 0. So yz plane, x is 0. So what left is 1 plus y plus z equal to 1. So again, y plus z equal to 1 is a straight line. Intersect at each axis at 1. So we have a straight line that. Okay, so this is y plus z equal to 1. And then we look at the xz axis, y is 0. Xy plane, y is 0. So y is 0, we have x plus z equal to 1. Again, you have slope negative. We have intersect at each axis at x equal to 1, z equal to 1 respectively. So we have that. So this is x plus z equal to 1. Okay, I think you can see now. Now x0, y0, z0. Z0 is on xy plane. Z0 xy plane. X0 on yz plane. Y0 on xz plane. So basically this solid is bounded by those for xz, okay, yz, I need different line, yz, okay, and xy. So what else like that? Xy. And then those what we call those things, all right, that surface. So that is a solid. So this is the solid. This is E that we mentioned in the theory. This is E that I mentioned in the beginning when I explained. In this case, in my case, it's V. All right. Now, what is D here? Or R in my case? All right. D or R. I use different notation. It might confuse you, but hopefully it's okay. In this case, D and R is just the same thing. Okay. Now, where is your R? R is we project from Z positive. You look at from Z positive on the XY plane. So what you see? We see this region. You see this region. Okay. Those surface we project on XY plane. So that's the region. So this is our D or R. Okay. Now to evaluate those integral, so we have integrate Z from base of the solid to the surface. The surface is given as we have Z from 0 to what? This is the surface. That surface is given as x plus y plus z equal to 1. You can write this as z equal to 1 minus x minus y. Okay, so now we have limit of integration z from base of that solid towards the surface. The surface is given by this. So we have z from 0 to 1 minus x minus y. Now for the second integral here, this integral we project on the xy plane. Okay, project on the xy plane, which is our region now is D. Okay, so D, we may take y from that line towards that line. So which is y from 0 to that line is given as y equal to 1 minus x. Y 1 minus x. Yeah, 1 minus x. Okay, so we have z, we have dz, we have dy, then we have dx. What about x? Limit for x. You look at this on x-axis. So it's from 0 to 1. So x from 0 to 1. Now, done. You can evaluate this. This part will give you z squared over 2. Okay, you have half z squared over 2. Your z is from 0 to 1 minus x minus y. I think you can do this. Then here we have half z is 1 minus x minus y squared minus 0. Okay, so this done for z. What left is x equal to 0 to 1, y equal to 0 to 1 minus x. Those function become there's a constant. I put it outside. Then we have 1 minus x minus y squared dy dz. Then you can do the rest of it. Okay, integrate iteratively. So for that case, we have what? I think you can factor out those things. Yeah, just factor out this. So we have 1 minus x plus y squared Yeah, right, so that give you 1 minus 2x plus y plus x plus y squared. Okay, that give you x squared plus 2xy plus y squared. Okay, so then you can simplify those things. X 0 to 1, y 0 to 1 minus x. So we have 1 minus 2x minus 2y plus 2xy plus x squared plus y squared dy dx. Okay, then you can proceed further. You can do that one. All right, so that's for the first case. Okay, for the second case, of course, is we look at the region D here, where in this case we project on xy plane. We can also do the projection on xz plane, where we look at it from y positive. Okay, or we can project on yz plane, where we look at the x positive. So each of those give you type 2 and type 3. So I think I don't want to give further the description on the type 2 type 3 region. You can look in the notes. I have explained those things. I hope you can understand. So I stop here for this for the video number 8. Thank you.